In 1971, Apollo 15 commander David Scott stood on the moon and dropped a hammer and a feather at the exact same time. Without air resistance to slow the feather down, both objects hit the lunar dust in a perfect tie. Newtonian physics explains this as a specific balance of properties. The moon's gravitational pull on the heavy hammer is far stronger than its pull on the light feather, but the hammer's higher mass also provides more resistance to being moved. In Newton's world, these two forces perfectly cancel each other out, every single time. By 1905, Albert Einstein's special relativity had successfully merged space and time into a single spacetime and established light speed as a universal limit. However, this new framework only applied to objects moving at a steady pace. It had no way to account for gravity. This created a conflict in the laws of nature. Scientists lacked a way to reconcile the universal acceleration of gravity with a relativistic universe that, at the time, only functioned for motion without acceleration. Explaining why a hammer and a feather fall at the same rate required moving away from the traditional model of an invisible pulling force. Imagine floating inside a windowless elevator in deep space, far from any planets. As the elevator falls freely, you would feel completely weightless, drifting inside the cabin without any sense of up or down. Now, compare that to a rocket accelerating at 9.8 meters per second squared. The floor pushes against your feet with the intensity of Earth's gravity. Einstein realized that without a window, resting in gravity and accelerating through space are physically indistinguishable. If being in free fall feels exactly like floating in zero gravity, then falling objects aren't actually being pulled by a force at all. Instead, they are simply moving along their own natural, uninhibited paths. From this perspective, what we perceive as the force of gravity is just the sensation of objects traveling unbothered through their local environment. But if objects dropped on opposite sides of the Earth are both traveling in straight lines without being pulled, why do their paths eventually converge at the Earth's center? Looking at a globe, two parallel lines starting at the equator and heading due north never turn, yet they eventually intersect at the North Pole. This convergence proves the surface they are traveling across is inherently curved. Einstein applied this logic to the four dimensions of spacetime. If freely falling objects converge toward the center of a planet, it is physical proof that the fabric of spacetime itself is curved. Gravitational attraction is a geometric result. Objects follow the straightest possible paths, called geodesics, through a warped environment. To make this theory useful, Einstein needed a mathematical way to calculate exactly how much a specific mass or energy warps the space around it. As spacetime curves near a massive object, a spherical cluster of floating particles will naturally compress inward, shrinking the entire ball. The shrinkage rate is determined by the energy density and pressure at the warp's center. Einstein's field equations formalize this relationship, creating a strict balance between the energy of matter and the geometry of space. This relationship establishes the core axiom of modern gravity. Mass tells spacetime how to curve, and this curvature of spacetime tells matter how to move. In a curved universe, gravity must affect everything traveling through the fabric of spacetime, even light, which has no mass. Starlight provides the proof. During a solar eclipse, astronomers can see light from distant stars bending as it passes through the curved space around the sun, shifting the star's apparent positions. This curvature also distorts time. In stronger gravitational fields, where the warp is more intense, clocks actually run measurably slower. While these effects are always present, they only become noticeably visible around objects of extreme cosmic density, where the geometric warps are most severe. General relativity is the active mechanical blueprint for the cosmos, governing the behavior of everything we observe. Einstein's theory led to one final extreme prediction. If spacetime is a physical fabric, then violently accelerating a massive object should cause that fabric to ripple. When two black holes merge, they send these gravitational waves radiating outward across the universe at the speed of light. As these waves pass through the Earth, they physically stretch and squash the dimensional fabric of our reality. The LIGO facility was built to detect these ripples. By measuring microscopic changes in the length of these massive tubes, scientists finally captured direct physical proof that space-time can be shaken. Gravity is the dynamic, geometric stage upon which the entire universe plays out, with every planet and star following the curves of a warped and shifting reality.